In this video, we discuss derivatives of inverse functions. We'll discuss how to determine if a given function has an inverse using calculus, how to create a restriction of a function so that the restriction has an inverse. And then we'll talk about computing the derivative of f inverse at a particular value of x. Then we'll also talk about how to derive formulas for derivatives of common inverse functions. The derivative of the inverse of e to the x is the derivative of natural log of x, or the derivatives of any of the inverse trig functions. So that's the plan. So let's start with just y equals x squared. So we all know that y equals x squared looks like this. I don't like the way those axes look. Now, this function actually doesn't have an inverse as it stands because it fails the horizontal line test. If I draw any horizontal line through this, where that horizontal line is given by an equation y equals c, where c is actually in the range of the function, that horizontal line is going to cross twice, right? Except for at y equals 0, then it'll only cross once. So this fails the horizontal line test, and it does not have an inverse. And I'm just going to abbreviate that HLT. But we still might be interested in finding a function that will undo this operation of squaring something. And I think most students, if you ask them, what's the inverse function of x squared, everyone will say, just take the square root of x. Squaring something and then taking the square root, those undo each other. Cubing something and then taking the cube root, those undo each other. Raising something to the fourth and then taking the fourth root, those undo each other. Say, but, we have to look at the original function. The problem with this is if I switch the roles of x and y, I don't actually get a function. What I get is a relation. So if I did switch the roles of x and y, we'd have something that looks like this. So instead of y equals x squared, we'd have x equals y squared. And we see that because y equals x squared fails the horizontal line test, the relation x equals y squared is not a function. We've got a vertical line that passes through that graph twice. This relation fails the vertical line test and is therefore not a function. And I'll abbreviate that BLT. That's really the whole point behind the horizontal line test. If a function fails the horizontal line test, when we write down the sort of inverse relation, the corresponding relation will fail the vertical line test because we switched the roles of x and y. But we might still want to find that inverse function. And we know that y equals the square root of x is probably that inverse function. But you might say, okay, well, how do I find that? How do I justify that if the function isn't supposed to have an inverse in the first place? Say, well, I can find an inverse if I restrict myself to part of this graph, and I want to restrict myself to part of the graph that sort of captures the entire range. So our range is 0 to infinity, and I'd like to find part of the graph that has the same range of 0 to infinity, but is either increasing the whole time or decreasing the whole time, so that the relation, so that the function is 1-to-1 and therefore has an inverse. So you've actually got a couple of options. The traditional choice, how do I say this? The conventional choice, mathematical convention, is to look at this restriction from 0 to infinity. So we'll restrict our graph, or we'll restrict this function y equals x squared. And I'll call it f of x equals x squared now. to the interval from 0 to infinity. If we do that, then you just have that right half of the parabola. So we've got y equals x squared for x greater than or equal to 0. Then every point in the range has a corresponding x value in the domain, and the function is 1 to 1. Now this passes the horizontal line test. Every horizontal line that we draw crosses the graph at most once. So this does have an inverse function. Okay, so it does have an inverse function. Now we can draw it. Okay, well, what does f inverse look like? Well, it's relatively easy to see. If you take this equation and solve for x as a function of y, this is what you get. Y equals x squared, where x is greater than or equal to 0, is equivalent to, well, if I solve for x equals the square root of y. And clearly, from the equation itself, we know that x is greater than or equal to 0 because this square root of y is always non-negative, right? But this expression, where x is a function of y and it's equal to the square root of y, is actually the same. If we graph it, it's actually the same set of points. So this isn't the inverse function. We don't actually get the inverse function until we switch the roles of x and y. If we switch the roles of x and y now, and then we call that y value f inverse, then we have y equals the square root of x, or f inverse equals the square root of x. And when we graph that, what we get is this. Since 0, 0 is on this graph, 0, 0 is on this graph, when x is equal to 1 here, y is equal to 1, so the point 1, 1 is on this graph as well. When x is equal to 2 here, y is equal to 4. So when x is equal to 4, on this graph, y is equal to 2, because you switch the roles of x and y, and you get that. So these two are inverses of each other. If we draw them on the same grid, we can see a little bit of symmetry. We have y equals, the square root of x, roughly. And y equals x squared. And if I had done a better job drawing my graph, we would see symmetry about the line y equals x. And that's always true for inverse functions. If AB is on the graph of f, then BA is on the graph of f inverse, excuse me. Okay, so that was a specific example. So how do we determine in general if a function has an inverse? Well, in our specific example, we applied the horizontal line test. This is a pre-calc concept. It says that if every horizontal line crosses the graph of f at most once, then f is 1 to 1 and therefore has a unique inverse. When we say at most once, we just mean if the horizontal line doesn't cross the graph at all, that's fine. For example, with this function, y equals -3 never crosses the graph because y equals -3 isn't in the range of the function. But if every horizontal line either crosses once or it doesn't cross, or crosses the graph once or it doesn't cross it at all, then we say that f is 1 to 1 and therefore has a unique inverse. When I say 1 to 1, that just means every x has only one y and every y has only one x. Now, every x automatically has only one y whenever you're talking about a function. when we are talking about a function that has an inverse, that every y also has to have only one x. Okay, so that's what we did using pre-calculus. We said, okay, well, how can we determine if a function has an inverse if we don't know what the graph looks like? If I don't have a picture in mind, well, then I can just use calculus. I'll compute f prime, and then if f prime is positive for all x in the domain, or if f prime is negative for all x in its domain, then f is 1-to-1 and therefore has an inverse. Now, if we're in one of these cases, we say that f is strictly monotonic. That just means the function is either increasing the entire time or decreasing the entire time, and it's increasing the entire time if f prime is positive for all x in the domain. It's decreasing the entire time if f prime is negative for all x in the domain. That just corresponds to this terminology. Then we say that f is strictly monotonic. And of course, it's implied that that's on its domain. If f is strictly monotonic, then f has an inverse. This just indicates that if the derivative changes signs, basically we're going to have a problem. Whoops. I tried to use this notebook. I think it was a bad idea. I see now why I should just use regular paper. I was like, I'm going to make a small book with a bunch of calculus in it, but that's cool, but you can't get to the bottom of the page, like the document camera can't see it. And you can't move the page up because it runs into the document camera. So let's look at that idea graphically. Instead of f is strictly monotonic. So here's a function that's increasing on its domain. Now y equals e to the x is an example. So f is increasing on the entire real line. Therefore, f is strictly monotonic. And therefore, f has an inverse. Or if a function is decreasing the entire time, I mean, it might look like that. So the slopes are always negative. Then we say f is decreasing on its domain. I'm just drawing a function with a domain of all real numbers. Therefore, f is strictly monotonic. Therefore, f has an inverse. You might say, well, why does that matter? Well, let's look at a graph that's not strictly monotonic. Let's say, okay, this function's decreasing for a while. We're fine, but now it starts to increase. Well, what happens there when it starts to increase? Well, at some point, well, we've got the derivatives are all negative, right? Because it's decreasing. And then here at the bottom, the derivative is 0. And then as soon as it changes directions, I can draw a horizontal line that passes through that graph twice. So now, because the function changed directions, because it went from decreasing to increasing, that function fails the horizontal line test and therefore is not strictly monotonic and therefore does not have an inverse as it's originally defined. So this function, let's say, I'll call this x naught, f decreases on negative infinity to x naught and increases shortly thereafter. So the function fails the horizontal line test and does not have an inverse on its original domain or its implied domain. And I just was starting to draw parabola, but we could have drawn a let's say cubic function. Then we'd have a problem up here as well. If, you know, if this function didn't turn around, all my horizontal lines would cross twice, right? But if it turns, well, now I've got horizontal lines that cross 3 times. So anyway, if the function's increasing sometimes and decreasing other times on the domain or on its domain, then the function does not have an inverse as it's written. So I hope that makes sense. I think that makes sense. So let's look at an example other than y equals x squared, because we already looked at that. Well, actually, let's revisit that one. So we have f of x equals x squared. Actually, I think I want to draw it like that. I want to try to draw a good graph this time. Try to keep all my tick marks evenly spaced. This is 1, 2, 3, 4. 1, 2, 3, and 4. And f of x equals x squared. It does not have an inverse as it's originally written on its implied domain of negative infinity to infinity. If we graph that, we know it fails the horizontal line test. At x equals 0, y equals 0. At x equals plus or minus 1, we get plus or minus 1 squared, which is 1. At x equals plus or minus 2, we get plus or minus 2 squared, which is 4. And it just continues. And so we've got options. We say, let's choose a restriction so that the function does have an inverse. And this is a technique that we can use in general, but we're just applying it to this particular example. I guess this is my advice on how to choose a restriction. And it's a restriction of the domain of f. I'm going to say so that the function, and I'm just going to call it f, has an inverse. Okay, so our goal here is to find that interval that captures the range of the function. So basically, you're just going to choose a part of the graph where the graph or the function values are increasing the entire time or decreasing the entire time, because basically we want to be either in this case or this case. We want it to be strictly monotonic. So we want to choose an interval where it's increasing, or we want to choose an interval where it's decreasing. But we also have this additional constraint. We want to make sure that we choose a restriction that captures the entire range. So I want to find a restriction that gives me all of the y values in the range of that function. So let's write that down. It's our goal. I want to restrict the domain of f to an interval where f is strictly monotonic, so increasing the entire time or decreasing the entire time. And the range of that restricted version of f is equal to the range of the original function. So we're trying to capture all the y values. We want all the same y values. You said, well, look at this function. What is the original range? Well, the original domain of f was all real numbers. The original range, well, that's a set of y values that have x values, right? Is 0 to infinity. So you actually have two options for this function. We could either make that traditional choice, that sort of mathematically conventional choice of restricting our function y equals x squared to the interval from 0 to infinity. If we choose that restriction, then y equals x squared, where x is greater than or equal to 0, has this as its inverse function. Y equals the square root of x. And you might be saying, okay, that's kind of obvious, but how do you know? How can you be sure that that's the one? Well, we're just switching the roles of x and y, remember? Now, notice that on this restriction of y equals x squared, x and y are both positive. So when we switch the roles of x and y will remain positive. So we're still in quadrant 1. And we've got some points on the graph. When x equals 1, y equals 1. When x equals 2, y equals 4. And so on. Now, when we switch the roles of x and y on this graph, well, 0, 0 is on both graphs. 1, 1 is on both graphs. And then since x equals 2, y equals 4 is on the graph of the original function, x equals 4, y equals 2 is on our graph. And so we have that as f inverse. Now I've written y equals x squared and y equals the square root of x, but I could have just as easily said f of x equals x squared and f inverse of x equals the square root of x. Those are our sort of traditional notations for f and f inverse. We like to give the functions a name instead of just calling them y, right? So that's one option. Now the other option is just to go the other way. Rather than restricting ourselves to this interval where the function happens to be increasing, and it does give us all of the y values in that range. So we get all the y's between 0 and infinity. We could also get all the y's between 0 and infinity if we chose the branch, or not the branch, it's one complete piece, isn't it? If we chose the interval where the function was decreasing the whole time. So we chose an interval where the function's increasing. So we wanted it to be strictly monotonic, and it is. And we got all the y values that we wanted from 0 to infinity. So this was a good choice. Well, the other option is to choose the decreasing branch. And for this particular function, the decreasing branch does give us all the y values that we want. We get all the y values between 0 and infinity, and that's fine. And it's decreasing the whole time, which means it's strictly monotonic. So that's our second option. Then y equals x squared, where x is less than or equal to 0, is our sort of restriction of that original function. Oops. And that implies that y equals the negative square root of x is its inverse. Okay, so if we want to graph this, it's relatively easy to do. All we have to do is graph that restriction. And then think about what happens when we change the roles of x and y. So I still have y equals 0 to, or we have y equals 0, y equals 1, y equals 4, all of the y values from 0 to infinity in our range. And we're talking about a part of the graph that is decreasing the entire time. So it's strictly monotonic. So this satisfies all of our requirements. And at x equals 0, we get 0. At x equals -1, we get 1, because -1 squared is 1. At x equals -2, we get 4. And so our graph looks like this. Now we're going to switch the roles of x and y. So on F inverse, well, on the original graph, 0, 0 was on our graph. So on the inverse graph, 0, 0 will also be on the graph. On the graph of the restricted y equals x squared graph, x equals -1, y equals 1 is on the graph. So then when we switch the roles of x and y, instead of having x equal to -1 and y equal to 1, we're going to have x equal to 1 and y equal to -1. So we're just sort of flipping that. Here we've got x equals -2, y equals 4 on the graph. If we switch the roles of x and y, we'll have x equals 4 and y equals -2 on the graph. And so we'll end up with that negative square root function. This is y equals the negative square root of x. This was y equals the positive square root of x. If we put those two pieces together, it's a little bit hard to see. It's not, I didn't make them symmetric. We get that parabola on its side, that parabola opening to the right. If we put these two pieces together, we get that parabola opening upward. But if we restrict this function y equals x squared to either the left half or the right half, we're able to get an inverse function, either the positive square root of x or the negative square root of x, depending on which restriction we choose. Now, concerning the derivative, if we are looking at the derivative of this function, and we're interested in how the derivative of this function relates to the derivative of this function, it turns out that they're going to be reciprocals of each other. So let's write that down. But I put a little star there. We need to be careful because you can't just plug in the same x value to this one that you plug in at this one. Here's the idea. If I compute the slope of this graph, y equals x squared at x equals 2, we all know what the slope will be. F prime is 2x. So if I evaluate that at x equals 2, I get a slope of 4. Oops. So I know that the slope at this point is 4. So I can write m equals f prime of 2, which equals 4. I'd say, okay, well, what does that tell us about the slope of sort of the corresponding point on the y equals the square root of x graph? Well, if we switch the roles of x and y, if 2, 4 is on the graph of the original function, 4, 2 is on the graph of this function, then at 4, 2, since the rate of change of this function is sort of that limit as delta x approaches 0 of delta y over delta x. So we're looking at the where the change in x goes to 0 of that change in y divided by the change in x. When we switch the roles of x and y, well, what we're going to get is instead of the change in y divided by change in x, we're going to get change in x over change in y. So the slope at this location is actually the reciprocal of the slope at that location. So since this original graph has a slope of 4, the inverse function at this point here actually has a slope of 1/4. But you have to be careful. If I look at the derivative of f inverse at x equals 2 and tell you that the derivative of f inverse at x equals 2 is 1/4, I'd be wrong. Because you actually have to change the x value. This says the derivative of the original function at x equals 2 is 4. When we switch the roles of x and y, we get that reciprocal slope, but it doesn't happen at x equals 2. It happens at x equals 4 on that inverse graph. So it's the slope at 2 is related to the slope at 4. Or the slope at 2 of the original function is related to the slope of f inverse at x equals 4. So you have, because you've switched the roles of x and y. So that's why we have that asterisk here. Let's try to say this a little bit more precisely. We'll say the derivative of f inverse at an x value in the domain of f inverse, which is actually a y value in the range of the original function. So at f of x is the reciprocal of the derivative of f at x. So here we have the derivative of f inverse at f of x equals 1 divided by f prime of x. Oops. So this evaluating at f of x and then evaluating at x is key. We have to substitute in the y value here to the in the derivative formula for the inverse function. So this is the derivative of f inverse at the y value on the original graph is equal to 1 over the slope of the original function at x. So we've got an x here and an f of x there. And this x value is in the domain of the original function. And this f of x value is in the range of the original function. And you might say, okay, well, that's nice, but how does that relate to the x and y values for the new function? Well, instead of evaluating the derivative of f inverse at f of x, where f of x is in the range of the original, or in the range of the original function, you can think of just evaluating f inverse of x, or the derivative of f inverse of x at x, where x is in the domain of f inverse. And say, okay, well, how can I write that down? I think I'll write it like this. I'll just use prime notation. The derivative of f inverse at x this time is the reciprocal of the derivative of f. But again, we have to be careful. Now I want to use an x value in the domain of f inverse. Well, this is going to be equal to the derivative of f at a y value in the domain of f inverse. So this is f inverse of x. Does that make sense? And that works because the range of f is equal to the domain of f inverse, and the I think I may have said that backwards. Yeah, the range of f, let me write this down. The range of f is the domain of f inverse, and the domain of f is the range of f inverse. And I think that makes sense because we've just switched the roles of x and y, right? So what used to be a y value for f is now an x value for f inverse. And what used to be an x value for f is now a y value for f inverse. So I can write this in terms of x's and y's that are in the domain and range of f, or I can write the formula in terms of x's and y's that are in the domain and range of f inverse. So either one is fine. And they're both accurate. They're equivalent to each other. It just depends on your perspective, which formula you're going to use. So that's our formula. We've got two equivalent forms. Let's actually use these formulas to compute the derivative of f inverse at a particular location. So we have the derivative of f inverse evaluated at f of x is 1 divided by f prime of x. So x is in the domain of f, and f of x is in the range of f, just sort of by definition, right? Or we can look at the derivative of f inverse at an x value, where that x value is in the domain of f inverse, and then we evaluate the derivative of f at f inverse of x. Either way is fine. So now we're asked to compute the derivative of f inverse at x equals 4. And I think that we can see what the answer is going to be. So here's our graph of f of x. We know when x equals 2, y equals 4. Then we said, okay, switch the roles of x and y. The corresponding point on the graph of f inverse is at x equals 4, y equals 2. Well, according to our formula, if I'm interested in the derivative of f inverse at x equals 4, I need to look at 1 divided by the derivative of f at the corresponding x value. Now, when x is equal to 4 on this graph, y is equal to 2. So when x is equal to 2 on this graph, y is equal to 4. So if I'm interested in f inverse at 4, I need to look at f at 2, compute its derivative, and then compute the reciprocal. Does that make sense? So we're linking the slope at x equals 4 on this graph to the slope at x equals 2 on that graph, because we switched the roles of x and y. Well, that's easy enough to do. F of x is x squared. So f prime of x is 2x. So we'll just have 1 divided by 2x, and then we'll evaluate that at 2. So we'll have 1 divided by 2 times 2, which is 1/4. You can say, oh, isn't there an easier way? Couldn't I just compute the derivative of f inverse in general? You'd say, well, yeah, sure. F inverse in this case was the square root of x, or x to the 1/2. What's the derivative of f inverse? I get, well, 1/2 times x to the negative 1/2, right? So that's 1/2 times 1 divided by x to the 1/2 if I use my exponent properties, because that x to a negative power is 1 over x to the same power but positive. And if we distribute, we get 2 times x to the 1/2 there. Now, if I evaluate that at x equals 4, I've got 1 divided by, or I can write it like that with square roots if I want to. I get 1 divided by 2 times the square root of 4, which is 2 times 2, or 1/4. So I get 1/4 either way. But you might say, okay, well, how are those related to each other? Well, what if we weren't at 4? What if I just wanted to relate these in general? I'd say, well, the derivative of f inverse at some x value in the range is 1 divided by f prime at f inverse. I said in the range, I meant in the domain. This is the domain of f inverse. And so you say, okay, well, how do we do that? Well, we compute the derivative of f, The derivative of f is 2x, right? But instead of substituting in a 2, I substitute in f inverse of x. And you say, well, what is f inverse of x? Well, f inverse of x is just 2 times the square root of x, right? Or excuse me, the f inverse of x is the square root of x. So I just have that, which is the same as what we got just using our formula, our power rule for derivatives. You may say, well, how is that related to the derivative of f in general? And say, well, I thought the derivative of f was 2x. Why do I have 2 times the square root of x? Why am I not getting the right thing? Well, it's actually because we're evaluating this at what was a y value, at a y value for f inverse, which was an x value for the original function. Say, oh goodness, what does that mean? Well, if I think of this as a y value, and this is actually f prime evaluated at y. And say, okay, well, what was f prime evaluated at y? That's 2y. And what is y on the graph of f inverse? It's square root of x. So we see that the derivative of f at x is 1 divided by f prime at y. So you just compute f prime, that's 2x. You replace the x with a y. And then you can substitute that y value that goes with that x value, or you can replace that y with whatever y is in terms of x on the inverse function graph. And you see that you get the same thing. Does that make sense? I hope it makes sense. And that's kind of what we did when we did this up here. We said, okay, I'm computing the derivative of f inverse at 4. Well, that's going to be 1 divided by f prime at the corresponding x value, which is 2. Well, what's the derivative of f at x equals 2? It's just 2 times x, which is 1/4. Or sorry, 2 times x, which is 4. Then we said we're going to take the reciprocal of that. We'll get 1/4. And that's going to be the derivative of f inverse at 4. So this tangent line has a slope of 4. And then this tangent line has a slope of 1/4. And I think that makes sense because basically this is change in y divided by change in x in an instantaneous fashion, but it's still change in y over change in x. And this is change in x divided by change in y. So I would expect the graph or the inverses to be reciprocals of each other. This might not be a very good example. Let's look at another example. So here we have f of x equals 1 divided by 27 times x to the 5th plus 2x cubed. We're asked to compute the derivative of f inverse at x equals -11. Now, if I could, I would just switch the roles of x and y. So this is my y value and these are my x values. Or excuse me, that's my y, and then of course I've got my x's over there. Sorry, what I just said didn't actually make any sense. If I switch the roles of x and y, I get this. X equals 1 divided by 27 times y to the 5th plus 2y cubed. Now at this point, if I wanted to find the inverse function, just using pre-calculus techniques, I would get y by itself, and then I would call this y value f inverse. So I'm going to say this is our equation where y is equal to f of x. And this is the relation satisfied where y is equal to f inverse. And you might say, how do I even know that f inverse exists? Well, we can verify that f inverse exists by computing the derivative. So we'll say the derivative of f at x is 1 divided by 27 times the derivative of x to the 5th, which is just 5x to the 4th by the power rule, plus 2 times the derivative of x cubed. So that's 2 times, well, using the power rule, we'll get a 3 out front, times x to the 1 less power. So we get that. Now, would you agree with me if I said that that's always non-negative? X to the fourth is always positive, x squared is always positive, except for when it's 0, right? So f prime of x is always greater than or equal to 0. So that means our function is either increasing or maybe momentarily at x equals 0, the derivative is 0. So the function is monotonic. Since that f prime is always greater than or equal to 0 for all real numbers x. And the domain of that function is all real numbers. And if f is monotonic, that means the function's increasing the whole time. It's 1-to-1. And if it's 1-to-1, that means it has an inverse. So we know that f inverse exists. And y equals f inverse satisfies the following relation. It's the equation that we get when we switch the roles of x and y. Okay, so we know that that's true. Now our goal is to find the derivative of f inverse at x equals -11. Well, in order to find the derivative of f inverse at x equals -11, we have to go back to this relationship. Well, x equals -11 is clearly going to be in, well, not necessarily clearly going to be in the range. But we want to substitute x equals a -11 here. But if we want to substitute x equals a -11 here, we need to find the corresponding y value for x equals -11. We say, okay, well, what is y equal to when x equals -11? Well, if x equals -11 here, that means that f of x equals -11 here. You say, okay, if f of x equals -11, what is x equal to? So either way, whether you think of that -11 as being a member of the domain of f inverse, or if you think of that -11 as being a member of the range of f, either way, you have to find sort of its partner. You have to find the x value that goes with that y value on the original graph, or the y value that goes with the x value on the new graph. So you say, okay, how do I find that? Well, let's write that down. We need to find the value of f inverse at 11, or at a -11. Once I know f inverse at -11, I can substitute that into the derivative of f. I can replace this x value with that y value on the graph of f inverse. And then that slope at that particular x value, 1 over that slope, is going to give us the derivative of f inverse there. Okay. Say, okay, I need to know what f inverse at -11 is. So I'll just say, let's let f inverse at -11 equal x. Then if we evaluate this expression, if we substitute this into the original function f and substitute this into the original function f, this is what we get. Struggling a little bit right now. Little notebook that sounded like a good idea to begin with, but I don't know if it is actually. So apply that function f to both sides of our equation. A little bit difficult to see, sorry. I don't know what's going on with my camera right now. Here we go. We'll say f of f inverse at -11 equals f of x. And f of f inverse at a value is equal to that value, because f and f inverse have the quality of undoing each other. So if I apply f inverse to this, I get some value, and then if I apply f to that, I get that value back. Well, then I know that the x value that we were looking for satisfies this. F of x has to equal -11. So we've got -11 equals 1 divided by 27 times whatever that was, x to the 5th plus 2x cubed. Say, I don't know what x values will give me a -11 over there. X equals 1 doesn't seem to work, because then I just have a 1 plus 2 is 3. So I'd have 3 divided by 27. It's definitely not -11. Why don't we try 2? Well, 2 is not going to work either, because if I substitute 2 in over here, I'm definitely not going to get a negative number. Why don't we try -2? I just have a tendency to try small integers and then just use common sense. We're trying to get a negative number out of this function, so put a negative number in. We're raising it to raising that number to odd powers. So a negative number raised to an odd power is another negative number. So I'll have 1 divided by 27 times -2 to the 5th plus 2 times -2 cubed. Let's see if that works. -2 to the 5th is -32. And then -2 cubed is -8. -8 times 2 is -16. So I've got -48 divided by 27. Did I do that correctly? Well, that is divisible by 3, and that's divisible by 3. So I'm going to have 3 times, what is that, 16? Divided by 3 times 9. So I don't get the right value. It's not -11. So I need my x value to be even larger than that. Let's try x equals -4. Or maybe -3. Let's try -3. Got 1 divided by 27 times -3 to the 5th plus 2 times -3 cubed. Now I am just sort of randomly guessing here. It's not exactly random, but I'm just guessing. This is going to give me, well, I know I'll have -3 to the 3rd is a -27. And then I'm going to multiply by -3 times -3, which is 9. And this is plus 2 times -27. And if I factor out that -27, we've got -27 divided by 27 times 9 plus 2. I think that gives us what we want, right? The 27's reduced and we get -11. So that checks out. So x equals -3 does give us a y value of -11 on the original function. So we have f of -3 equals -11. And that means f inverse of -11 equals -3, because we switched the roles of x and y. If we wanted to graph it, we could. So I want my x's to go all the way out to -11. And I want my y's also to go all the way down to -11. 1, 2, 3, 4, 5, 6, -7, -8, -9, -10, -11. And this tells us that when x equals -3, y equals -11 on the graph of the original function. And this tells us on the graph of the inverse function, when x equals -11, y equals -3. So again, we see some symmetry about the line y equals x. Since AB is on that graph, BA is on that graph. So this is on F inverse. This is on F. Okay. So I want the derivative of F inverse at -11. In order to find that, I look at the derivative of F at -3. So I say, well, what is the y value, or what is the x value that goes with this y value on the original graph? And the x value that goes with this y value is -3. Or we can say, what was F inverse of -11? It was -3. Either way. Say, okay, well, what is F prime of x? Well, it's the derivative with respect to x of that 1 divided by 27 times x to the 5th plus 2x cubed. And we've already done this. We got 1 divided by 27 times 5x to the 4th plus 6x squared. So when we evaluate at -3, we get 5 times -3 to the 4th plus 6 times -3 squared. And again, I see that 27 out front. I'd like to be able to simplify that with this. So I've got 1 divided by 27 times 5 times -3 cubed is -27. And then we're going to multiply by an extra -3. And this 6 I can think of as 2 times 3. This is 2 times -3 squared, which is 9, times that extra 3, which is going to be a 27. So I've got a 1 divided by 27 times -27 times -15. And then if we want, we can say plus 2 times 27. If we factor that 27 out, we'll have a negative times a -15 is positive 15 plus 2. Those guys reduce. And we get a slope of 17. I hope I did my arithmetic correctly. Say, okay, if the slope here is 17, which is huge, I was going to try to graph it. I'm just going to do a cartoon. M equals 17. Did I do that correctly? Yeah, this is a 27. Then we're going to have a 3 and the 5. It's going to give us the 15. Okay. All right. We got 17 there. If this function has a slope of 17, over here, we're going to have a slope of 1/17. So here we would go up 17 and over 1. Over here, we're going to have to go up 1 and over 17. So the derivative of F inverse at -11 is 1 divided by 17. I say, oh, that's really tedious. And we weren't even able to find F inverse. And because when we look at that graph, or when we look at that equation, that comes from switching the roles of x and y, we actually can't solve for y. I can't get y by itself unless I know how to solve for this, sort of get rid of that 5th power of y. And you say, well, just take the 5th root. Well, I can't. If I take the 5th root of that, then I end up with this 5th root of the y cubed. If this term was missing, we could solve for y. But since I have the y to the 5th term and the y cubed term, I can't get y as a function of x, not explicitly. But I know that F inverse exists because the derivative of F is always non-negative, which means it's monotonic. So F inverse exists. So if we switch the roles in x and y, since this function was increasing, the F inverse function will also be increasing. And I think that makes sense because the derivatives are reciprocals of each other, right? if this is always greater than or equal to 0, when I take the reciprocal, I'm always going to get an answer that is also greater than 0. Now, when this function is 0, we'll have a derivative that is undefined for f inverse. So we might have a vertical tangent line when x equals 0 on the graph of f inverse, or at the y value corresponding to x equals 0 on the graph of f inverse. And it just so happens f of 0 is 0. So since the point is 0, 0 anyway, we just know that f inverse should have a vertical asymptote at x equals 0, whereas this one has a horizontal asymptote at x equals 0. But since this is positive all the time, the derivative of f inverse should be positive. But you say, okay, how do I find an equation for f inverse if I can't even find out what f inverse looks like? When I was able to solve for f inverse here, I had f inverse equals the square root of x. I could just use the power rule and compute the derivative. So is there a way to find a formula for f inverse in general? So, well, yeah, we already learned implicit differentiation, right? And I know that y equals f inverse satisfies this relation, or it's not just a relation, it's actually an equation that defines a function, f inverse. You say, well, how can I find the derivative of that function? We'll just use implicit differentiation. And whenever we have that dy dx, remember that y is actually f inverse when we're talking about a y value that satisfies this equation. So let's do that. That'll give us a formula for f inverse. Now we're not just finding sort of those ordered pairs. So I've got x equals 1 divided by 27 times y to the 5th plus 2y cubed. It's doing that glare thing again. So what I'm trying to do is find a formula for the derivative of f inverse using implicit differentiation. I don't know why my camera is doing that. Say, okay. Well, when we're using implicit differentiation, we just take the derivative of both sides with respect to our independent variable. And just remember that y is actually a function of x. The derivative of x is 1. And the derivative of this expression is 1 divided by 27 times the derivative of y to the 5th with respect to x. Now, if I take the derivative of y to the 5th with respect to x, or y is a function of x, I actually have to use the chain rule and have 5 times the inside function raised to the 4th. And you say, well, what's your inside function? Well, it's just y of x. And then you multiply by dy dx, where y is f inverse. And then here we do the same thing. That should be a 3y, what's it? 2y cubed, sorry. Now when I take the derivative of 2y cubed with respect to x, where y is a function of x, I've got to use the chain rule as well, because y is actually a function of x. So we'll have 2 times 3, which is 6, times y to the 1 less power. So we're putting our inside function back inside, and then we're multiplying by the derivative of the inside by the chain rule. And you don't have to write y of x explicitly, I just choose to. Now, if you factor out dy dx on the right-hand side there, you end up with 1 divided by 27 times 5y to the 4th plus 6y squared. Is that the same derivative we had earlier? Did I write the problem down correctly? All of this is multiplied by dy dx. So we have dy dx equals 1 divided by 1 over 27 times 5y to the 4th plus 6y squared. All right, so that is the derivative of f inverse, because remember, y is actually equal to f inverse. So this is the derivative of f inverse at a particular x value. It's 1 divided by 1 over 27 times 5 times y to the 4th plus 6 times y squared. But you might say, well, what is y squared, and what is this y value? Well, it's actually f inverse at x. Now you can think about it that way if you want to. So you say, what's the derivative of f inverse at a particular x value? Well, it's 1 divided by this expression. You say, okay, well, that kind of reminds me of something, right? I've seen that before, that 1 over 27 times the quantity 5y to the 4th plus 6y squared, haven't I? Actually, yeah, we have. That is this guy. Remember f prime? It was 1 over 27 times 5x to the 4th plus 6x squared. So it looks like all we did was we took f prime, and then instead of evaluating it at x, we evaluated at a y value, and that y value is a y value on the graph of f inverse. So an alternative form of this is to say, well, dy dx, or the derivative of f inverse at x, is just 1 divided by the derivative, how do I say this? The derivative of x with respect to y, where x is a function, the function relating x and y is that one that we get when we switch the roles of x and y. Say, okay, I switch the roles of x and y, I get this relation. And so now x is a function of y rather than having y as a function of x. Well, I just take the derivative of x with respect to y, I compute that, 1 over that turns out to be the derivative of y with respect to x. I think that's cool. I think that's really cool. You might say, it kind of looks like I just took this dy dx and I flipped it. Like if I have 1 divided by a fraction, I just multiply by the reciprocal, right? And so I just get the reciprocal, I just flip it. It's like, yeah, that's actually what we did. Except we're not thinking of it as a fraction, we're thinking of it as a new function. So we had y as a function of x was 1 over 27 times x to the 5th plus 2x cubed. If we switch the roles of x and y, we have x as a function of y is 1 divided by 27 times y to the 5th plus 2y cubed. If I take the derivative of that and I substitute it there, well then the derivative of f inverse is actually 1 divided by the derivative of that. That makes sense. I hope it does. Or alternatively, you could just compute y prime for the original function and then replace the x's with y's, and you get the same thing. I hope that makes sense. In this notation, it looks worse. But with this notation, I think it makes sense. You just have to remember this y is actually f inverse. And this y is actually the value of f inverse at the x value where we're evaluating that derivative. So you still have to think about that relationship between the x's and the y's, which was sort of described over here. Ah. All right. So what's my claim? So that reciprocal relationship we talked about holds. And you can get that derivative, you can get a formula for that derivative in terms of the y values on the graph of f inverse relatively easily. You just switch the roles of x and y, compute the derivative here, plug it in, and then you will have the derivative of f inverse, not in terms of x, unfortunately, but in terms of the y values on its graph. So that is the same, or so this equation is telling you the same thing as this equation. And we were able to find that equation using implicit differentiation. To get a better sense of this, let's look at Desmos. Let's graph this. And we'll have a better idea of what's going on. I have a tendency to think this way of switching the roles of X and Y in calculus 2 a lot. But this is a little bit different because when we solve an equation for X in terms of Y versus Y in terms of X, we actually don't change the graph at all. They're the same locus of points. But what if we switch the roles of X and Y, if we actually write X instead of Y and Y instead of X, well, that gives us the inverse relation. And if that relation happens to be 1-to-1, then we call that the inverse function of the original function. So I'm gonna have X here, Y here. This is f of X equals 1 divided by 27 times that X to the 5th plus 2y cubed. Oops, I wrote y cubed, I meant X cubed. So we've got that. Its derivative is well defined all the time. We were able to find it relatively easily. We get 1 divided by 27 times 5x to the 4th plus 6x squared. We can look at the graph and we can see it's non-negative. It's always greater than or equal to 0. It's only equal to 0 at x equals 0. So our derivative is well defined. The only issue is that we have this horizontal tangent line at x equals 0. Now, if we switch the roles of X and Y, we get an inverse function. Now, I don't actually know how to solve for X, or I don't know how to solve for F inverse, where Y or F inverse is a function of X, but I know an equation that will be satisfied by F inverse. So let me first replace F with Y. And so we just get y equals 1 divided by 27 times that x to the 5th plus 2x cubed. And we see it's the same as the original graph. We haven't changed anything. But then we're going to switch the roles of x and y. As soon as you switch the roles of x and y, that y is not the same y as before. It has the same values as before, but now that y is no longer y equals f of x. We're going to call that y f inverse. So I'll have x equals 1 divided by 27 times y to the 5th plus 2 y cubed. Now, this is a function. You can tell that it's a function just by looking at it. Every x value has only one y, and every y value has only one x. And we also know that it has, or we know that this is, or this set of points represents a function. Because the derivative of f was always non-negative, we see that this function is going to have a well-defined derivative for all real numbers except for at x equals 0. When the original function f had a tangent line that was horizontal, so a tangent line with a slope of 0, the f inverse function is going to have a vertical tangent line. So we're going to have a tangent line that has an undefined slope at x equals 0. But otherwise, I mean, this is a function. And we can think of this as x as a function of y, just to almost turn your head sideways. And you say, look, there's x as a function of y. It's pretty much the same function as before. I've just drawn it sideways and then sort of flipped it so that our x and y are both positive in that top right quadrant, as opposed to having x and y both positive in the bottom right quadrant. So we see that x is a function of y. And what function of y is it? It's this 1 over 27 times y to the 5th plus 2y cubed. So this is an equation that is satisfied by y equals f inverse. We'll write that down. Okay, so we know that that's true. So how do you find the derivative of f inverse? Well, compute x prime of y. If this is x of y, then compute x prime of y. See if Desmos likes that notation. It does not like that notation at all. So I'll just call this x prime of y. So I have 1 divided by 27 times 5y to the 4th plus 6y squared. And then the derivative of f inverse is the reciprocal of that. Okay. So now let's go back to that original question. The original question said, let's see, this is our problem statement. I'm going to type it in. Given f of x equals this function, compute the derivative of f inverse at x equals negative 11. You say, okay, well, I need to find the value of f inverse at x equals negative 11. Well, when x equals negative 11, we know that y has to satisfy, well, negative 11 has to equal 1 divided by 27 times y to the 5th plus 2y cubed. So that equation needs to be satisfied. So we just need to solve for y. We solved by just choosing some y values or choosing just some values to plug in over here. And we said, okay, x equals negative 3 works, right? And then when we plugged in, I think it was negative 3. We just guessed a couple of y values. And then we found a y value that worked. And we said, okay, that'll work. And then once we found that y value, we evaluated the derivative here. Alternatively, you can think of that as the x value on the corresponding graph of the original function f. But either way, you're taking f of x and you're setting it equal to negative 11, or you're taking x of y and you're setting that equal to negative 11, and then you're solving this equation. So you're either solving negative 11 equals 1 divided by 27 times x to the 5th plus 2y to the 3rd, where x is in the domain of f, or you're solving negative 11 equals 1 over 27 times y to the 5th plus 2y to the 3rd, where y is in the range of f inverse. But the range of f inverse and the domain of f are the same thing. So I mean, you're still just looking for the partner of this x to the x equals negative 11. That x equals negative 11 is that x value in the domain of f inverse. So basically, we're just trying to find f inverse at that particular point. Now, we can do that a little bit more systematically than we did on paper, using what's called possible rational roots. Let's do that. So we're trying to solve negative 11 equals f of x, or negative 11 equals, what is that, f inverse of y? Is that right? It's not f inverse of y. It's actually f of y, isn't it? So we have negative 11 equals 1 divided by 27 times 5x, or excuse me, x to the 5th plus 2 y cubed. Actually, I don't want to use that notation here. Okay, I scratched that out, but maybe I shouldn't. I was just saying that negative 11 equals f of y, or y is f inverse. So I've got f of y and this is f inverse of x, but our x value is -11. So we get f of f inverse of -11 is -11. So of course that's satisfied, but we're saying, okay, but what is f of f inverse of -11? We're calling that y. We're saying, what's that? So either way, whether you say -11 equals f of x or -11 equals f of y, you're solving this equation, with either an x to the fifth and an x cubed, or a y to the fifth and a y cubed. It just depends on what your perspective is, whether you're thinking of that x value as being in the domain of f, or if you're thinking of that as a y value in the range of f inverse. Same thing. Say, okay, well, how do I solve this? How can I solve this more systematically? Well, we could add 11 to both sides. And then we could multiply both sides by 27. So you get x to the fifth plus 2x cubed plus 11 times 27. And then we can use what is called possible rational roots. I actually use this a lot in differential equations when we're solving polynomial equations. So I've got a polynomial equation. I want to know what the roots of that polynomial equation are. Again, roots are just x values that cause a polynomial to be 0. And it turns out that the possible rational roots of a polynomial equation with rational coefficients are given by the factors of the constant term divided by factors of the leading coefficient. The constant term in this case is 11 times 27. And the factors of the leading coefficient are, well, it's just the factors of 1. Okay, well, what are the factors of 11 times 27? Well, I guess you could use plus and minus 1 and plus and minus 11 times 27, whatever that number is. And then you could have plus and minus 3. And then you'd have, well, 27 is, actually, let's factor that. We've got 11 times 27, which is 11 times 3 times 3 times 3. So I could have plus or minus 3 times, well, if I get rid of the 3, 11 times 9. So plus or minus 99. 4 is not a factor. 5 is not a factor. 6 is not a factor. We don't have another factor until we get a 9, right? So we could also just factor out a 9 here. So we could have plus or minus 9. And then if we factor out a 9, we have plus or minus 33. And say, okay, 11 is a factor. Then plus or minus 11 and plus or minus 27. 12, 13, 14. We're not going to have any other factors until we get to 27, right? And we have 27 and then 11. I think those are it. That's our list. So if I look 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. None of those are factors of this. And then the factor after 27 is at 33. So this is our list of possible rational roots. We have a lot of them, 1, 2, 3, 4, 5, 6, 7, 8 possible rational roots, times 2 because you could have positive or negative roots. So you have 16 possible roots. And you might say, oh, that's a lot of numbers to check. You said, well, yeah, it is a lot of numbers to check. But now instead of checking just any number we want, instead of just checking randomly, we know that if this function has any rational roots, it's on this list. So if I had created this list to begin with, I never would have tried x equals -2 because x equals -2 isn't even on the list. I was tempted to try x equals -4, wasn't I? But x equals -4 wasn't on the list. If I write this list of possible rational roots first, then I know I'm not going to make the mistake of trying x values that couldn't possibly satisfy this equation. So I said, okay, well, this is my list. I like to stick with small integers. I would normally try plus or minus 1 just in my head to substitute 1. Well, I get 1 plus 2 plus that number. It's definitely not 0, right? Now, another thing I notice when I look at this equation, this polynomial equation on the right, I see that we have positive coefficients in all cases. So if all of those coefficients are positive, I'm supposed to get 0 over here. The x value that I have to substitute here must be negative. so that when I take that negative number and raise it to the fifth, and I take that negative number and cube it, I actually get a negative number to cancel out that negative, or that positive 11 times 27. So I know I'm looking for a negative root. And I know if I plug in negative 1 for x, I get negative 1 minus 2. So that's just negative 3 plus a number that's, very large compared to negative 3. So plus and minus 1 are out. And we could literally substitute that and simplify, but we can substitute that in our minds, in our heads, and we can see, yeah, I'm not going to get anything here. If I substitute x equals positive or negative 1, that will cancel this 11 times 27. So you say, okay, well, let's go to the next integer. I wouldn't want to try this next. Let's try, plus or minus 3. And then you say, well, I don't want the positive 3 because I know I won't get a 0 if I substitute in positive 3. Let's try the negative 3. So we'll take negative 3 and we'll raise it to the fifth. And we'll add 2 times negative 3 cubed. And then we'll add 11 times 27. And our hope is that we get 0. So you say, okay, well, what is that? Well, I don't know. I guess you could say it's 81 times 3. But I'm mostly interested in those factors that multiply to give me 27. And I know 3 times 3 times 3 is 27. So I'll think of that first. This negative 3 to the fifth, I'm thinking of as negative 3 cubed times a negative 3 squared, because this is 5 negative 3's multiplying each other. So I've got negative 3 cubed times negative 3 squared plus 2 times negative 3 cubed plus 11 times 27. And when I do that, when I recognize it that way, this becomes a negative 27 times 9 plus negative 27 times 2 plus 11 times positive 27. Well, if I add this negative 27 times 9 to the negative 27 times 2, I get positive 11 times negative 27. And I'm adding 11 times 27. And so I get 0. And that's cool. Then I didn't even have to work out what 11 times 27 was. I can just, knowing how this factors, I can see that I'm going to get a 0 there. So what does that mean? That means that x equals negative 3 is a root of the polynomial equation. And so what does that mean for our functions f and f inverse? Well, it means that f of negative 3 is equal to negative 11, and f inverse of negative 11 is equal to negative 3. So when x is negative 11 in f inverse, the y value is negative 3. When x is negative 3 in f, the y value is negative 11. You say, okay, well, how is that relevant again? Okay, we were asked for the derivative of f inverse at negative 11. Our derivative rule says just evaluate 1 divided by the derivative of f at negative 3. Which is the same as what we see here, which is the same as what we see here, where this y value is the y value on f inverse. And the y value on f inverse is just the x value that goes with y equals negative 11 on the original graph. So you just find its partner, and then evaluate the slope of the original function at that value, and simplify. And we already done this. F prime at negative 3 was 17, I think. So we got 117. So we talked about how to determine if a function has an inverse using calculus. We just compute the derivative if it's positive all the time or negative all the time. Then we know the function is strictly monotonic and therefore has an inverse, and that inverse is well defined. If we have a derivative that is non-negative, so it's sometimes 0, then our derivative of f inverse will be well defined, except for when the derivative of f was 0, because then we'd have 1 divided by 0 there. That just means we're going to have a vertical asymptote somewhere on the graph of f inverse. So where the original function had a horizontal asymptote, when you switch the roles of x and y, the f inverse function is going to have a vertical asymptote. So we talked about that, talked about finding a restriction. Basically, you choose a restriction of f that gets you all the y values and is 1-to-1. So we're looking for the function to be increasing on that entire interval or decreasing on the entire interval and still giving us all of the y values of the function. And we said that we can compute f inverse at a particular x value by looking at the derivative of f at the corresponding y value and then taking the reciprocal of that. Now, with all of that said, now we can derive some formulas for the derivatives of some inverse functions, some commonly known inverse functions. We've got y equals natural log of x and all of those inverse trig functions. I think this is pretty cool. When I looked at this, I thought it was really neat. And this is closely related to this, very closely related. But you want to be careful. With this one, you actually have to switch the roles of x and y so you get a different curve. Now, when you're evaluating these expressions here, where we're deriving the formulas for the derivatives of these inverse functions, we're not actually going to get a different curve. We're going to write the same curve or write an equation for the same curve in a different way. So let's do that. Let's do that for natural log of x first, and then we'll do that for the inverse trig functions. Now, we already know a few things about e to the x. We know that the derivative of e to the x is e to the x. And we've already talked about the fact that the derivative of natural log of x is equal to 1 over x. So we know that those things are true. But you might say, okay, since those are inverse functions of each other, can I derive that another way? I think I may have just told you that this was true. I'm not sure if we derived it. We may have derived it. I don't remember. But we can derive it if we look at sort of the corresponding equations for, or two different equations, two unique equations, not unique equation, two equations, two ways of describing the same set of points. So let's look at y equals the natural log of x now. And y equals the natural log of x looks like this. When x equals e, we have the natural log of e. We say e to what power is e? Well, e to the first power. It's about 2.7-ish, right? And if we evaluate natural log of 1, let's say what's natural log of e? Natural log of e is some number. That's equivalent to saying e to what power is e? Whenever we are evaluating a logarithm, we're thinking of that question. Saying e to what power is that? Well, the first power. So natural log of e is 1. And then when I'm computing natural log of 1, well, that's going to be a number. And the way we figure out what that number is we think in terms of exponentials. We say, well, e to what power is 1? We know that e to the 0 power is 1. So natural log of 1 must be 0. So here's our logarithm graph, y equals natural log of x. Now, if I want to, I can solve this for x by exponentiating on both sides. If y equals natural log of x is equal to e to the y. So those are two equations. They describe the same set of points. If I graph this in Desmos and I graph this in Desmos, I get the same curve. I have not changed the roles of x and y. I have just written the equation in terms of x. I've written y as a function of x and I've written x as a function of y. But either way, we get the same set of points. So this particular point on the graph of y equals natural log of x can be written, well, as xy in general, but it can be written entirely in terms of x if I let my x be x and I let my y be natural log of x. Or it can be written entirely in terms of y. I can let my y be y and let my x equal e to the y. But either way, those describe that same set of points, x, y, where y is equal to natural log of x and x is equal to e to the y. You say, well, how does that help us? Well, if I want the derivative of natural log of x with respect to x, turns out I can just compute 1 over the derivative of the corresponding function with respect to y. So this is saying that dy dx is equal to 1 over dx dy. So I've got y as a function of x is natural log of x. So that the derivative, that's my dy dx here, where y is natural log of x. And the claim is that that's the same as 1 divided by the derivative of x with respect to y. And x is e to the y. Does that make sense? So I'm just saying dy dx is 1 divided by dx dy. And that's true as long as y of x and x of y describe the same set of points. So these are just two equations that describe the same set of points. Say, okay, well, let's actually compute that. Well, what's the derivative of e to the y with respect to y? It's just e to the y, right? And then you say, well, what is e to the y in terms of x? Well, e to the y is x, right? So the derivative with respect to x of natural log of x is 1 over y. So we've derived that formula using that fact that dy dx is equal to 1 over dx dy. So that's one way of doing that. I guess we could have gone the other way as well. Well, what's the derivative with respect to x of e to the x? Instead of looking at this graph, we could have looked at this graph when x is equal to 0, y is equal to 1 on the graph of e to the x. And when x is equal to 1, y is equal to e on the graph of e to the x. So my graph for e to the x looks like this. Well, according to that formula, the derivative with respect to x of e to the x is 1 divided by the derivative with respect to y of the corresponding function. Well, if y is equal to e to the x, if I take the logarithm of both sides, I get x is equal to natural log of y, right? So those are equivalent to each other. Take the natural log of y on the left-hand side, and if you take the natural log of the left-hand side and the natural log of the right-hand side, we have natural log of y equals the natural log of e to the x, which is just x, because those functions undo each other. So the claim is that the derivative of this function with respect to x is equal to 1 over the derivative of this function with respect to y. Well, we just derived the derivative of natural log of y. We said that that was 1 over, the derivative of natural log of y with respect to y is just going to be 1 divided by y. Just replacing that x with a y instead of, replacing this with a y and that with a y. So it's just a dummy variable now. We know that the derivative of natural log of x with respect to x is 1 over x, so the derivative of natural log of y with respect to y is 1 over y. 1 divided by 1 over y is just y. And you say, well, what is y in terms of x? Well, it was e to the x. So the derivative of e to the x is e to the x. So that's another way of sort of computing that derivative. Now we can do the same thing with all of our inverse trig functions. So let's look at y equals sine of x. You might say to yourself, does that function y equals sine of x have an inverse? And this function repeats itself, right? Okay, well, no. As it stands, as it traditionally stands, it does not have an inverse, because if I draw any horizontal line where y is equal to constant, and that constant is between -1 and 1, that horizontal line is going to cross the graph of y equals sine of x infinitely many times. Way too many times for this function to have an inverse. So we say, okay, we can't, this function does not have an inverse as it's originally written, excuse me. But if we take the restriction, and we take a restriction that gives us all of the y values in our range from -1 to 1, well, then the function will have an inverse. You say, okay, well, which restriction should we take? Let's take the same restriction as everyone else. All the mathematicians got together a long time ago and they said, we're going to be interested in the restriction from -π/2 to π/2. Let's take that restriction, because sine of -π/2 is -1. Sine of π/2 is +1. And as x goes from -π/2 to π/2, we get all the y values between -1 and 1. This is just mathematical convention. We could have just as easily chosen an interval where the function was decreasing. So we could have chosen the interval from π/2 to 3π/2. And then we would have all the y values between -1 and 1 as well. But we all agree that we're going to take that interval, and we're going to switch the roles of x and y. And when we switch the roles of x and y, what we get is this. Now, first of all, if I took the original function y equals sine of x, and I just switched the roles of x and y. So I have x equals sine of y. I would not have a function. I would have a relation, and it's going to look like the sine function just turned on its side. So I'm going to have something that looks like this, and then like this. It's a little bit difficult to draw. Oops, so that's at pi. I didn't do a very good job drawing that graph. It doesn't look like a sine when you look at it on its side. But the function goes up first, and at, that should be 2 pi, sorry. At pi over 2, the corresponding x value is 1, and then at pi it crosses the y-axis. And then at 3 pi over 2, the corresponding x value is -1. And so you see that 0, 1, 0, -1, 0. But we've switched the roles of x and y. I mean, over here we had 0, 1, 0, -1, 0. We switched the roles of x and y. It looks like 0, 1, 0, -1, 0. And of course, that's happening at 0, pi over 2, pi, 3 pi over 2, and 2 pi. Just like here we have 0, pi over 2, pi, 3 pi over 2, and 2 pi. So we've switched the roles of x and y, and this is what we get. But again, that's not a function. But it will be a function if we just look at this restriction of this. We took the restriction of sine of x to the interval from -pi over 2 to pi over 2, and then we switched the roles of x and y. So we're only interested in the part of this graph where x goes, or where the y values go between -pi over 2 and pi over 2. So our restricted domain is -pi over 2 to pi over 2. And of course, the range of our restriction, we want that to stay the same as it was before, from -1 to 1. When we switch the roles of x and y, the domain of our inverse function is the range of the original function. So our domain is -1 to 1. So we've got all the x values between -1 and 1 here, because we had all the y values between -1 and 1 here. And the range of this function corresponds to the domain of this function, but it's not the domain of the original function. It's the domain of the restriction, which we chose to be -pi over 2 to pi over 2. We say, okay, with that in mind, we're going to, x equals sine of y is this black curve, but y equals arc sine of x is that blue curve. And the arc sine of x has as its domain the interval from -1 to 1, including the endpoints. And it has as its range the interval from -pi over 2 to pi over 2. So those are the y values that we get from this. Okay, so you might say, how do I find the derivative of arc sine of x? Well, if y equals arc sine of x, if I take the sine of both sides, I have sine of y equals the sine of the arc sine of x. Since the sine and the arc sine undo each other, we just have an x on this side. So I have sine of y equals x when y equals arc sine of x, provided that our y value here is in the interval from -pi over 2 to pi over 2. And the x value, of course, has to be in the domain -1 to 1. So you say, well, what's the derivative of arc sine of x? Well, it turns out to be 1 divided by the derivative with respect to y of sine of y. Now, my claim is that these are two different ways to represent that same curve. We're just looking at that blue part of the curve. If I take the sine of both sides, I get this equation. So these equations are actually equivalent to each other, provided that our y's are in the appropriate range. So y has to be between -pi over 2 and pi over 2, and x has to be between -1 and 1. So that's true. Then you say, okay, well, what is the derivative with respect to y of sine of y? It's cosine of y. Say, okay, well, what's cosine of y? Well, I'd like to write my final answer in terms of arc sine of x, or in terms of x, because I'm taking the derivative with respect to x of arc sine of x. And my x value is actually sine of y, because these two equations are equivalent to each other. So rather than having this cosine of y in the denominator, I would really like to have a sine of y in the denominator instead. Well, I can find that sine of y in the denominator if I remember this fact. I know that sine squared of y plus cosine squared of y equals 1. I know that's always true. It's going to be true for any angle, right? So if I wanted to, I could solve this for cosine of y. Cosine squared y is going to equal 1 minus sine squared y. And the cosine of y in general is going to be plus or minus the square root of 1 minus sine squared y. Now, you might say, okay, what is the sign, the SIGN sign of this? I don't actually get two values in the denominator. I only get one value. Well, in order to figure out whether I should get the positive square root or the negative square root, I need to look at the cosine of y on this interval, or the cosine of y, or alternatively, the cosine of x on this interval from negative pi over 2 to pi over 2. Because remember, this cosine of y is just like a cosine graph turned on its side. I'm really thinking more in terms of cosine of x, where cosine is on the same graph as the original sine function here. So you say, well, what does cosine look like? Well, it starts at its max, then it's 0, then it goes to its min, then it's 0, and then it goes back to its max. So it looks like this. And I'm interested in the cosine of y on the interval from negative pi over 2 to pi over 2, right? So if I continue that graph, it looks like that. Okay, so I'm just interested now, not in cosine of y in general, but in the restriction of cosine of y to negative pi over 2 to pi over 2, because that is the range, or excuse me, that is the range of this arc sine of x function, but it's the corresponding domain of that restricted sine function if I go back to my restricted function that I started with. So you say, okay, on the interval from negative pi over 2 to pi over 2, is cosine of y positive or negative? Well, on the interval from negative pi over 2 to pi over 2, cosine is positive, right? We can see the y values are positive on that cosine graph. So I'm going to take the positive square root here. So this is 1 divided by the positive square root of 1 minus sine squared y, or I can call that sine of y squared. You said, but what is sine of y in terms of x? Well, sine of y is x. So I get the derivative with respect to x of arc sine of x is 1 minus this 1 divided by the square root of 1 minus x squared. So that's nice. That's really nice. Now, the only tricky part was thinking about that plus or minus, but it's relatively easy to figure out whether that's plus or minus this expression by looking at the cosine function on the interval of interest from that original graph of that sine of x. Before we look at sine of x and then we look at cosine of x, but we're only interested in that on that interval that we restricted it to before we took the inverse. Say, okay, can we do the same thing for the derivative of arc cosine of x that we did for arc sine of x? Say, yeah, sure. What do we need to keep in mind? If we're looking at arc cosine of x, y equals arc cosine of x. And say, well, what do we know about arc cosine of x? If I take the cosine of both sides, I've got cosine of y equals cosine of the arc cosine. And the cosine of the arc cosine of x is just x because those two inverse functions undo each other. So these guys are equivalent as long as our y values are in the range, or excuse me, yeah, they're in the range of the arc cosine graph, which comes from the restricted domain of that cosine graph. Now, you have to remember what that restricted domain was in order to sort of look at the appropriate interval and say, well, how do I know what that is? Well, your trig teacher usually tells you. The cosine graph looks like this. Goes from to its max to 0 to its min, back to 0, and then back to its max. And all the interesting things happen at 1/4 of the period, and the period is 2 pi. So it looks like this. When we came up with the arc cosine function, everybody agreed we needed to choose an interval that captures all of the y values. All the y values on the cosine graph are between -1 and 1. We know that. Well, some mathematicians got together. I actually don't know the history, but I always imagine that some mathematicians got together and they said, let's just restrict ourselves to the interval from 0 to pi. So we're going to let y equal, or x equal cosine of y, but we're only interested in y values that are between 0 and pi. If we restrict ourselves to the angles between 0 and pi, we get all of the cosine values between -1 and 1. So y equals arc cosine of x is equivalent to cosine of y equals x, as long as our y values are between 0 and pi and our x values are between -1 and 1. Okay, so what's the derivative of arc cosine of x? Well, I claim it's 1 divided by the derivative with respect to y of cosine of y. Because this is y equal y as a function of x, so we're taking the derivative with respect to x of y. And here we're taking the derivative with respect to y of x. So I've got y as a function of x here, x is a function of y here, and we're just saying dy dx is equal to 1 over dx dy. Say, well, what is dx dy? Well, the derivative of cosine of y with respect to y is negative sine of y. You say, okay, negative sine of y. What is that in terms of cosine? Well, I can find negative sine of y in terms of cosine of y, just by using this equation again. We know that sine squared y plus cosine squared y equals 1. So sine squared is equal to 1 minus cosine squared y. And sine of y is equal to plus or minus the square root of 1 minus cosine squared y. So you'd say, okay, but what is sine of y on the interval of interest? We want to restrict ourselves to the interval from 0 to pi. Well, if I look at the interval from 0 to pi, what do we know about the y values on our sine graph? Well, in the interval from 0 to pi, the y values are all positive, right? Or non-negative. They're between 0 and 1. Since our y value, or the y values on the sine graph are all non-negative on that interval from 0 to pi, we just take the positive square root here. That negative I'll put in the numerator. And so sine of y is the negative, or is a positive square root of 1 minus cosine squared y. And we said, well, what is cosine of y? It's x. So this is -1 divided by the square root of 1 minus x squared. So notice the derivative of arc sine of x is 1 divided by the square root of 1 minus x squared, and the derivative of arc cosine is the same, but with a negative sign. That negative comes from the fact that the derivative of a cofunction is always -1 times a function. All of our cofunctions have negative derivatives. Derivative of cosine is negative sine. The derivative of cotangent is negative cosecant squared. The derivative of cosecant is negative cosecant cotangent. The other three derivatives are all have a positive sign out front, a positive 1 as the coefficient of the trig function. So that's how we compute the derivatives of arc sine and arc cosine. We can do the same thing with arc tangent and arc cotangent. So if we're interested in the derivative of y equals arc tangent of x. Now, if we take the tangent of both sides, we have the tangent of y equals the tangent of the arc tangent of x. And the tangent of the arc tangent of x is just x. So I'm going to use a little bit different notation here and say y of x is arc tangent of x, and x of y is tangent of y. Now, both of those are the same set of points, provided we look at the restriction. And when we computed the inverse function, when we defined this inverse function arc tangent of x, we actually restricted ourselves to the interval from negative pi over 2 to pi over 2. Since I'm taking the tangent of y here, I'm restricting my y values to be between negative pi over 2 and pi over 2. So these are y values in the range of arc tangent of x, as opposed to y values or x values in the domain of tangent. So the tangent graph looks like this. It has asymptotes at x equals negative pi over 2 and pi over 2. And the function repeats, right? You just keep seeing that same pattern over and over and over again, infinitely many times. If we try to find an inverse function for y equals tangent of x, we're going to have a problem, because that horizontal line is going to cross the graph infinitely many times. We see here, if we look at 3 branches, it crosses 3 times. But if we restrict ourselves to this one branch between negative pi over 2 and pi over 2, then that function is 1-to-1. It does have an inverse. The range is all real numbers. Now, when we switch the roles of x and y, where this function, y equals tangent of x, has vertical asymptotes, x equals negative pi over 2 and x equals positive pi over 2, when we switch the roles of x and y, our inverse function will have horizontal asymptotes at y equals negative pi over 2 and y equals pi over 2. Now, if I am sort of thinking about that inverse function, I sort of imagine like turning my head sideways and then graphing this. So typically, if I were to graph this, I might just graph it like this. But then my x and y would be positive in this quadrant, so I have to flip it. So it's going to look like this. This is y equals arctangent of x. And the domain of arctangent is the range of tangent. And that's all real numbers. And the range of arctangent is the domain of that restricted tangent function. Which is negative pi over 2 to pi over 2. So inverse trig functions give you angles. The output is always an angle. And you say, well, what is that angle? It's an angle in that restriction, the restriction of the original function. So arctangent of x is going to give me an angle between negative pi over 2 and pi over 2. Arcsine of x is going to give me an angle between negative pi over 2 and pi over 2 inclusive. Arc cosine of x gives me an angle between 0 and pi inclusive. So you say, okay, well, how can I use that to compute the derivative of arctangent now? Well, the derivative of arctangent, so it's the derivative of y as a function of x. This is my y of x. It's going to be 1 over the derivative with respect to y of x as a function of y. Well, if y is equal to arctangent of x, x is equal to tangent of y. So I'm just taking the derivative of tangent of y. And you're saying to yourself, what does that mean again? Well, this is y equals arctangent of x. That's equivalent to, if I take the tangent of both sides, x equals tangent of y. So this is x as a function of y, this is y as a function of x, and they were saying dy dx is equal to 1 over dx dy. Say, well, what is the derivative of a tangent of y with respect to y? Well, it's secant squared y, we know that rule. But we'd like to know what that is in terms of tangent, right? Because tangent of y equals x, and we'd like the derivative of arctangent of x in terms of x. You say, well, okay, well, what is secant squared in terms of tangent? Well, secant squared is 1 plus tangent squared. That's one of our identities. You can take that sine squared of y plus cosine squared of y equals 1 and divide both sides by cosine squared y, and you'll get this equals that. You say, okay, this is 1 over 1 plus tangent squared y. And what is tangent of y? Well, it's x. Now, again, these are not inverse functions. These are two different ways to describe the same set of points. In both cases, I'm talking about this set of points. So this just comes from rearranging this equation to solve for y. So those are equivalent to each other. Say, okay, well, this is 1 over 1 plus tangent squared y, where tangent of y equals x. So that's 1 over 1 plus x squared. So the derivative of arctangent is 1 over 1 plus x squared. If I want to take the derivative of arc cotangent of x, that turns out to be 1 over the derivative with respect to y of cotangent of y. Because if arc cotangent of x equals y, then x is equal to cotangent of y. So if y is this function of x, and we take the cotangent of both sides, we have cotangent of y equals x. Does that make sense? Okay, and you say, well, what's the derivative of cotangent? Well, that's negative cosecant squared y. And say, okay, well, how is that related to cotangent of y? Well, we know that cosecant squared is 1 plus cotangent squared. I'll put that -1 in the numerator. We can find that identity by taking that sine squared y plus cosine squared y equals 1 and dividing both sides by sine squared y. If you divide term by term by sine squared y, you get 1 plus cotangent squared equals cosecant squared. You say, but what is cotangent of y again? Well, that's x. So x is a function of y, and this is y as a function of x. So derivative of y with respect to x is equal to derivative of, or 1 over the derivative of x with respect to y. Cotangent of y is equal to x. I get -1 over 1 plus x squared. So the derivatives of arctangent and arccotangent are almost identical. We have a 1 over 1 plus x squared and a -1 over 1 plus x squared. And that negative comes from the derivative of that cofunction having a negative sign out front. But we use very similar identities. We're just using Pythagorean identities that all came from that sine squared y plus cosine squared y is equal to 1, or I'm thinking sine squared theta plus cosine squared theta equals 1, where theta is an angle. In this case, the y values are angles because we're looking at the y values on inverse trig functions, and inverse trig functions always give us angles because the tangent of that angle is going to give us that x value. You say, what angles are we interested in? Just the angles from the restriction, that -pi/2 to pi/2. Those are the y values that we get in the range of this arctangent graph. You say, well, oh, they're just numbers. Well, yeah, they're numbers. But I find that if I think of them as angles as opposed to thinking of them as just numbers, it helps. It helps keep track of things. It helps us to remember that the inverse trig function should always get us some expression, usually involving pi, right? Something like that. But it's sort of a familiar number in radians. So we're used to, pi/2, pi/4, multiples of pi/3 and pi/6, or those quadrantal angles. But we always have to look at the restriction here. You say, well, what is the restriction for cotangent? Well, with cotangent, that cotangent graph actually looks like this. It looks a lot like tangent, but instead of being increasing, it decreases. It has asymptotes at x equals 0, x equals pi, x equals 2 pi. It actually has asymptotes at all of the multiples of pi. So we say, okay, does that have an inverse? No, not technically. It fails the horizontal line test. But if I restrict myself to the interval from 0 to pi, then it does have an inverse. So you say, okay, let's look at this restricted domain. Look at cotangent. On the restricted domain of 0 to pi, then the range of that cotangent is still all real numbers. So we're getting all the real numbers from that interval from 0 to pi. And then we switch the roles of x and y to get the arc cotangent function. So the when I switch the roles of x and y, the range of the cotangent becomes the domain of the arc cotangent. So we can put in any real number we want because we got any real number we wanted out of that cotangent graph. And then the domain of the restricted domain of the cotangent becomes the range of the arc cotangent. So we're going to use 0 to pi here. Now I want you to notice that as x approaches 0 from the right, the y values go to infinity here. So as y approaches 0, our x values should go to positive infinity. It's kind of hard to draw. I'm trying to make sure I draw it correctly. Now, as x approaches pi from the left, the y values go to negative infinity. So as the x values go to negative infinity, the y values approach pi. So this had vertical asymptotes at x equals 0 and x equals pi. The arc cotangent function has vertical asymptotes or horizontal asymptotes y equals 0 and y equals pi. And so you imagine graphing this just sort of sideways, but make sure if you were to draw it over here, it would end up in the wrong quadrant. So you have to flip it across the y-axis and then make sure the behavior is correct. It's a little bit tricky. I like to think of this way: as x approaches 0 from the right, y goes to infinity. So when we switch the roles of x and y, we have as x goes to infinity, y should approach 0 from above. And so that gives us that behavior. And here I said as x approaches pi from the left, y goes to negative infinity. So as x goes to negative infinity, y approaches pi from sort of below. Now this looks a little weird. We're not used to writing from the right or from the left when we're talking about sort of the range variable. We're used to just talking about approaching a number from the right or the left in the domain. But in principle, it's the same. This is just saying we're approaching pi from values that are less than pi. And here we're approaching 0 from values that are slightly greater than 0. Okay, and that's our derivative. Now we can do the same thing with the arc secant function and the arc cosecant function. So let's do that. Now, in order to do that, it's helpful to look at the secant graph. Now, I actually don't remember what the secant graph looks like off the top of my head unless I graph the cosine functions. The cosine looks like this. And then it repeats itself. So it starts at its max, then it's 0, then it goes to its min, then it's 0, and then it's its max. And then it goes back to 0, then it's min, then it's 0, and then it's max. So this is y equals cosine of x. Now, the secant of x is 1 divided by cosine of x. So whenever cosine of x is 0, the secant graph is going to have vertical asymptotes. So I draw those vertical asymptotes through all the zeros of the cosine function, which occur at odd multiples of pi over 2. And then when cosine of x is 1, secant's going to be 1 divided by 1, so we'll get 1. And then if we look at the y values here, as we approach negative pi over 2 and pi over 2 from the right and left respectively, we're dividing by tiny positive numbers, so we get large positive numbers. Here, when cosine of x is negative 1, we have 1 divided by negative 1 for secant, so we get a negative 1 for the secant value. And then as we approach our asymptotes, we're dividing by tiny negative numbers because that cosine value is negative there. 1 divided by a tiny negative number is a large negative number, so those are going to negative infinity, and that pattern repeats. So then you say to yourself, okay, does this secant function have an inverse? And you say, no. There's a horizontal line that crosses infinitely many times. It crosses there and there and there and there, and it continues. And I can draw horizontal lines down here as well. That's going to cross infinitely many times. You can also draw horizontal lines between -1 and 1. They're not going to cross the graph at all, and that's fine. But we say, okay, this does not have an inverse as it stands, but I'd like it to have an inverse. Can I restrict myself to an interval where this secant graph does have an inverse? And we say, yeah, we can. Let's look at the part of the secant where the secant is increasing. So we're going to look at this part and this part together. So our restriction is going to have two branches. And we're going to restrict ourselves to the interval from 0 to pi. And the reason I'm choosing that is because all the mathematicians do. We're going to go from 0 to pi over 2, and then union pi over 2 to pi. I'm really thinking of the interval from 0 to pi, but we skip that pi over 2 because we've got an asymptote there. And then the range of the secant graph, remember that's all the y values that have x values. If we go from the bottom to the top, we go from -infinity to that y value, which is -1. And then we skip all the y values between -1 and 1, and then we go from y equals 1 to infinity. Okay, so now we're going to switch the roles of x and y to draw the arc secant graph. The domain of the arc secant is the range of the secant function. So it's going to be from -infinity to -1, union 1 to infinity. And the range of the arc secant is the domain of the restricted graph. So we're going to go from 0 to pi over 2, and then pi over 2 to pi. Say, okay. Well, what is this point? This is x equals 0, y equals 1. So if x equals 0, y equals 1 is on the secant graph, when I switch the roles of x and y equals 0, x equals 1 is on our restricted graph. Now this function has a vertical asymptote, x equals pi over 2. So when we switch the roles of x and y, our graph is going to have a horizontal asymptote, y equals pi over 2. This was 0, 1, and this is 1, 0. Now this is the point x equals pi, y equals -1. If we switch the roles of x and y, we have x equals -1, y equals pi. And now we want to make sure our graph approaches the asymptotes in the appropriate way. So I'm going to look at this graph and I'm going to describe that behavior of the secant function in terms of x and y, and then we'll switch the roles of x and y. So we'll say as x approaches pi over 2 from the left, the y values go to infinity. So over here, as x goes to infinity, the y values approach pi over 2 from the left. Now, when I say pi over 2 from the left, it's not really left anymore. It's sort of from the bottom, from y values that are below pi over 2. So as x goes to infinity, we're going to approach pi over 2 like this. So this part of the graph corresponds to that part of the graph. You say, okay, what happens on this branch? As x approaches pi over 2 from the right, what happens to the y values? They go to -infinity, right? Well, switching the roles of x and y, we have as x goes to -infinity, y approaches pi over 2 from the right. So we're going to go to -infinity, and the y values on our graph are going to get close to pi over 2, but they're going to be slightly greater than pi over 2. So it's going to look like that. So that comes from this part of the graph after switching the roles of x and y. So this is y equals arc secant of x. And remember, arc secant is going to give you an angle. That angle is between 0 and pi, and it's never equal to pi over 2 because secant of pi over 2 is not well defined. Okay, so now we've got that. Keep all that in mind. And now we'll say the derivative of y with respect to x is equal to 1 over the derivative of x with respect to y. And if we have y equals arcsecant of x, if we take the secant of both sides, we have the secant of y equals the secant of the arcsecant of x. And the secant of the arcsecant of x is just x. So now you've got two different ways of describing the same function, or excuse me, the same set of points, and we're talking about this set of points. Y as a function of x is arcsecant of x, and x as a function of y is secant of y. But of course, we're not just talking about the secant of y in general, because that's going to look like these sort of parabolas that are opening up and down, except our parabolas would open left and right. If I were to just draw secant of y without the restriction, I'd have a parabola. It's not a parabola. It's like sort of a U shape opening up, and then a U shape, or a U shape opening to the right, and then a U shape opening to the left, and then open to the right, and then open to the left, and open to the right and left. We'd have the same patterns over here. So we would just sort of see that, but flipped, where if I completed that graph, it would look like that. You see those U shapes? So that's what we would see. But I'm thinking of x, or y is a function of x here, and x is a function of y here. So my y is a function of x is arcsecant of x. And x is a function of y is secant of y. Those are the same set of points. The derivative of y with respect to x is 1 over the derivative of x with respect to y. Say, okay, well, what's the derivative of secant of y? It's secant of y times tangent of y. Say, okay, I'd like to write that not in terms of secant and tangent, but I'd like to write it in terms of secant of y, because secant of y is actually equal to x, and I'd like a function of x here. Say, how can I get that? How can I get what I need? How can I get what I want? Well, I know that tangent is related to secant by the following identity. We know that if we take sine squared y plus cosine squared y equals 1, and we divide everything by cosine squared y, this is what I mentioned earlier in this video. If we simplify, we get sine squared over cosine squared is tangent squared y. Cosine squared over itself is 1, and 1 over cosine squared is secant squared. So tangent of y can be written in terms of secant of y by taking this equation and rearranging it. And if I subtract 1 from both sides and take the square root, don't forget the plus or minus, you get plus or minus secant squared y minus 1. Or plus or minus the square root of secant squared y minus 1 is tangent of y. So we end up with 1 divided by secant of y, and I'll put that plus or minus out front, plus or minus secant of y times the square root of secant squared y minus 1. Say, okay, how do I know whether it's going to be plus or minus secant of y? How can I tell whether that sign is going to be positive or negative? Well, I need to look at the sign of this product, secant of y times tangent of y, on this interval from 0 to pi. So we know that secant looks like this. We're on the interval from 0 to pi. And we've got that asymptote at pi over 2. Secant looks like this on that interval. I drew that graph in black. This is the restricted secant function. On the same interval, I want to draw my tangent function. I still think of my tangent in terms of those branches on the interval from negative pi over 2 to pi over 2, and then the next branch on the interval from pi over 2 to 3 pi over 2, and so on. So secant actually looks like this. And of course it repeats. Okay, what does our tangent graph look like on that interval, or on those intervals? Tangent looks like that. But again, we want to restrict ourselves to this interval from 0 to pi. So we're looking at secant times tangent on the interval from 0 to pi. So this is the secant part, the part of the secant graph we're interested in, the part of the tangent graph we're interested in. This is the part of the tangent graph we're interested in, and the part of the secant graph we're interested on the interval from pi over 2 to pi. So what is secant times tangent? What is the sign of that on that interval? Well, this is going to be a positive times a positive on this first interval, so we should get a positive answer there. And then on the interval from pi over 2 to pi, we've got a negative times a negative, so we should get a positive number. So what is that plus or minus secant of y going to be? Well, it's just going to be the absolute value of secant of y. Because this square root of secant squared y minus 1 is always positive, and I want my answer to be positive all the time. So let's just find secant of y, take its absolute value. Isn't the absolute value of secant of y equal to plus or minus secant of y, depending on what the sign of secant y is? Sure, it sure is. So we've got this answer, which is positive, times this square root, which is always positive. And you say, well, what is that in terms of x? Well, what was secant of y in terms of x? Well, it was x, right? So this is 1 divided by the absolute value of x times the square root of x squared minus 1. And again, you say, where did that absolute value come from? It came from the fact that we had to do tangent equals plus or minus this square root. And tangent is positive sometimes and negative sometimes on the intervals of interest. You said, but when I look at the product, secant times tangent, secant, we've got a positive times a positive, which should be positive, or a positive, or a negative times a negative, which should be positive. And that tells us that when we take this plus or minus secant of y, we should just replace it with the positive answer that we would get, which is the same as the absolute value of secant of y. Okay, so the derivative of arc secant is this 1 over the absolute value of x times the square root of x squared minus 1. Let's do the same thing for arc cosecant. Now, if you're thinking to yourself, which restriction do they take for arc cosecant? It's usually the same as the restriction for the corresponding reciprocal function. Since we take the restriction of sine on the interval from negative pi over 2 to pi over 2, when we take the restriction of arc cosecant to get the, or when we take the restriction of cosecant of x in order to get the arc cosecant graph, we use that same interval. So we're going to relate this to, we're going to relate the arc cosecant of x to the cosecant of y. But we're on the interval from pi over 2 or negative pi over 2 to pi over 2. Say, okay, well, what does that look like again? Okay, well, in order to graph the cosecant function, I always look at the sine function first. So my sine looks like this. And it repeats. So it's equal to 0 at negative pi and 0 and pi and 2 pi and so on. And to graph the cosecant, this is y equals sine of x. To graph the cosecant function, I'm graphing 1 over sine of x. So I'm going to have asymptotes on the graph of the cosecant function, whatever sine of x is 0. So we have asymptotes at all the multiples of pi. So negative pi, 0, so that's on the x or y axis, then at pi, then at 2 pi, and so on. And then we've got 1 over sine of x. When sine of x is 1, we've got 1 divided by 1, so we get 1 for our cosecant graph. And then as we approach 0 and 2 pi, or excuse me, 0 and pi, from the right and left respectively, we're going to have 1 divided by a tiny positive number, so we're going to get a large positive number. Now, at negative pi over 2, sine of x is negative 1. So 1 divided by negative 1 is going to give us a negative 1 for the cosecant of x at negative pi over 2. And then as we approach negative pi and 0 from the right and left respectively, we're going to have 1 divided by a tiny negative number, because the y values on the graph of the sine are tiny negative numbers at that point. 1 divided by a tiny negative number is a large negative number. So we get something that's that sort of U shape again, looks like that. And of course, this thing repeats itself. And so on. So we say, does it have an inverse? No, it fails the vertical line test, or excuse me, the horizontal line test. This fails the horizontal line test. So if we switch the roles of x and y, the corresponding graph would the corresponding graph of the inverse relation would fail the vertical line test, and it wouldn't be a function. So we say we've got to restrict ourselves to some interval. Which interval are we going to restrict ourselves to? The same one that we restricted ourselves to for sine. So when we took the restriction for sine of x to get all of the values in the range, and we looked at negative pi over 2 to pi over 2. Instead, we're going to look at the same interval from negative pi over 2 to pi over 2, but we have to exclude x equals 0 because the cosecant is undefined at x equals 0. So the restricted domain is the interval from negative pi over 2 to 0, union 0 to pi over 2. So I'm still thinking negative pi over 2 to pi over 2, the restriction for sine of x, but I exclude 0 because of the asymptote. And the range of the cosecant graph for the restriction that we're interested in, well, it's negative infinity all the way to negative 1. And then we skip all the y values between negative 1 and 1, and then we go from 1 to infinity. So we say that's pretty cool. All right. Now, what about the arc cosecant graph? In order to graph that, we say that the range of this restriction is the domain of our arc cosecant. So the range before was negative infinity to negative 1 and 1 to infinity. So I'm going to be looking at this graph on the interval from negative infinity to negative 1 and 1 to infinity. But I'm interested in my range being negative pi over 2 to pi over 2, excluding 0. So I'm going to go from negative pi over 2 to pi over 2. And say, okay, this restriction of the cosecant graph has a vertical asymptote x equals 0. So the arc cosecant graph, instead of having a vertical asymptote at x equals 0, the arc cosecant graph will have a horizontal asymptote at x equals, or at y equals 0. And say, okay, well here it says when x equals negative pi over 2, y equals negative 1. If I switch the roles of x and y, when x equals negative 1, y will equal negative pi over 2. So that's going to be a point on our graph. And here, when x equals pi over 2, y is equal to 1. So now when we switch the roles of x and y, when x is equal to 1, y will be equal to pi over 2. You say, okay, well, what about those limiting values? All right, well, we're approaching 0 from the left and right, correct? So we're going to have as x approaches 0 from the left, the y values go to negative infinity. So when I switch the roles of x and y, as x goes to negative infinity, y will approach 0 from the left, or from below. So it's going to be, the y values are going to be slightly less than 0 as x goes to negative infinity. So we have that. So this branch here becomes this branch here after we switch the roles of x and y. Now here we see as x approaches 0 from the right, the y values go to positive infinity. Now we're going to switch the roles of x and y. We'll say as x goes to positive infinity, y will approach 0 from above. So we're going to go to the far right. And as we go farther and farther to the right with our x values, the y's are going to approach 0, but from above that x-axis. So that's the arc cosecant of x. And you say, how do I find the derivative of arc cosecant? Well, the derivative with respect to x of y of x is equal to 1 over the derivative with respect to y of x of y, where these two equations, y equals arc cosecant of x and x equals cosecant of y, are two different ways to describe the same set of points. Say, okay, well, what is the derivative of cosecant of y? It's negative 1 times cosecant of y times cotangent of y. And cosecant of y is x. So I'd like to write everything here in terms of cosecant of y. rather than in terms of cotangent of, or a cosecant of y and cotangent of y. Well, we can do that. And write that -1 in the numerator. If I take my sine squared y plus cosine squared y equals 1, and instead of dividing by cosine squared this time, I divide everything by sine squared. We have 1 plus cotangent squared y equals cosecant squared y. So this cotangent of y can be written in terms of cosecant of y if we rearrange this identity. I want to get cotangent of y by itself. So I'll say cotangent of y is equal to, subtract this 1 from both sides, don't forget your plus or minus. Cotangent of y is equal to plus or minus 1, or cosecant squared y minus 1. So we're going to have here -1 divided by plus or minus cosecant of y times the square root of cosecant squared y minus 1. Now, to figure out what to do with that plus or minus in front of the cosecant of y, we will look at the graphs of cosecant and cotangent on the interval of interest. We've actually already got the graph of a cosecant on the interval from -π/2 to π/2, but I'd also like to look at the graph of cotangent. Now, remember what cotangent does? Cotangent looks a lot like the tangent function, but rather than increasing on every branch, it decreases on the branches, and cotangent is undefined whenever sine is 0 rather than when cosine is 0, because cotangent is cosine divided by sine. So these cotangent branches look like this. You say, okay, but I'm not interested in the whole thing. I'm only interested in that part on the interval from π/2 to or -π/2 to π/2. So I'm interested in that part here and that part here. Say, okay, well, on the interval from 0 to π/2, this cosecant of y times cotangent of y is a positive times a positive, so we should get a positive answer in that denominator. And then on the interval from -π/2 to 0, we've got a negative times a negative. Negative times a negative should be a positive, so we'll have a positive down here, and that -1 in the numerator stays the same. So this should always be positive when we take the product, of course, except for when it's 0. But when these are both negative, well, you see what the pattern is. So this should be a negative times a negative is a positive, and this is a positive times a positive is a positive. So this product in the denominator should be positive, and the square root is always positive. So we're going to write that plus or minus cosecant of y as the absolute value of cosecant of y. And you say, well, what is cosecant of y? It's x. So this becomes -1 divided by the absolute value of x times the square root of x squared minus 1, because x is our cosecant of y. Notice that that is the same form of the derivative for our arcsecant, but with our arcsecant, we just had a positive 1 in the numerator, whereas with our arc cosecant, we get a -1 in the numerator. That negative comes from the derivative of our cofunction being negative, having that -1 factor out front. So you can memorize those rules. We've got the derivatives of all 6 inverse trig functions, but they're really sort of 3 derivatives: the derivative of arcsine, derivative of arctangent, and the derivative of arcsecant. And then the derivatives of the arc cofunctions, arc cosine, arc cotangent, and arc cosecant look just like the other derivatives, but with a -1 in the numerator rather than a positive 1. And that -1 factor comes from the derivative of a cofunction having a -1 factor in it. All right. So that is the end of our discussion over the derivatives of inverse functions. Now, this was only tangentially related to what we were talking about with the derivatives of inverse functions earlier, as it's a little bit different. These aren't exactly inverse functions. They're just 2 different ways to describe the same set of points, but it's very similar to what we did with the inverse functions. With the inverse functions, we took the derivative of f inverse and we related that to the derivative of f. And we said, okay, well, when does that equation hold? Well, that equation holds the derivative of f inverse at f of x is equal to 1 over the derivative of f at x. Or we can say the derivative of f inverse at x is 1 over the derivative of f at f inverse. either way, whether we look at the XY pairs in terms of F inverse or in terms of F, you sort of have to work with the X value and Y value on this side and this side when you're looking at the derivatives of inverse functions. But with these other functions, the inverse of the exponential function being the logarithm, and then the 6 inverse trig functions that go with our trig functions, we actually we don't have to worry about that XY issue as much. This equation, y or x equals cosecant of y, describes the same set of points as y equals arc cosecant of x. These are just rearrangements of the same equation. I've just solved for y as a function of x or x as a function of y. And what we've done in the last 7 examples, as we said, the derivative of y with respect to x has to be 1 over the derivative of x with respect to y when x of y and y of x describe the same curve. And we were able to do that for all of those functions and get our derivatives in terms of x. So I think that's pretty cool. That's it. Let me know if you have any questions.